Suppose we have a road that follows a parabolic path, y equals x squared, from x equals -1 to x equals +1. One question we might be interested in knowing is how long is that path? How far is that car going to travel? How much asphalt do we need to pave the road? Stuff like that. So we can clearly approach this using incremental measurements, right? We could say, well, maybe just approximate the curve using straight lines. Okay, so maybe connecting one endpoint to the middle and then the middle to the other endpoint using 2 partitions, or maybe using 4 partitions, or maybe using 8 partitions. And you can see that if n equals 2, we get a fairly close approximation, but not nearly as close as if n equals 4, because this length is much closer to the curve. There's still a bit of a problem here, right? But we can eliminate a lot of that problem by changing n equal to 8. So the idea is the same as what we've always been doing in calculus. We start with an approximation, and then we make it a better approximation, and a better approximation, and even a better approximation until we make it as good as possible. So for our convenience, I've went ahead and calculated these approximations using the distance formula, right? So this first one we can talk about real quick. The change in x and the change in y are both 1, so this diagonal distance is √2, and this diagonal distance is also √2. So the s is approximately equal to 2 √2, which is 2.83. Now we can do the same thing with more partitions, but it's going to get pretty tedious, right? So we're using the distance formula, which is the Pythagorean theorem, to find the distance between each of the 2 sets of endpoints, right? So x sub 0, y sub 0, comma x sub 1, y sub 1, use the distance formula. And then from x1, y1 to x2, y2, use the distance formula again, rinse and repeat. So in general, we find x sub I minus x sub I minus 1, and we square that. We take y sub I minus y sub I minus 1, and we square that. And we take the square root of that. That's the Pythagorean theorem, or the distance formula. We do this for each of the subpartitions. So I don't know why this is such a long radical. We didn't really need that. So let's go ahead and make a new one and say, well, a more convenient way of doing this is saying, well, this is the distance between 2 different consecutive x values, so we'll call it delta x. The ith delta x value, we'll square that, and then the ith delta y value, and we'll square that. And that's just going to be for each I value throughout the interval, right? And we'll do that 2 times, or 4 times, or 8 times, or however many times we want to do that. Small values of n are clearly not desirable because of inaccuracy. It's not a very good approximation with small values of n, but of course large values of n are not desirable because of tedium, right? We don't want to sit here all day using the distance formula over and over again. We could build a program, maybe program a spreadsheet to do this. That wouldn't be too terribly difficult. But we are in the business of getting exact values, so we're going to go ahead and use calculus to find an exact value. So what we're going to do is we're going to say, well, we've got this this sum of n line segments lengths, and we're going to try to deal with this. So one thing we can try is we can factor out the delta x. So I'm going to go ahead and factor out that delta x, not out of the sum, although if delta x is constant throughout, I suppose we could factor it out. But we're going to go ahead and factor out inside the square root still. This expression has a delta x sub I squared in the first term. If we factor it out, we're left with 1. We're dividing it out of the first term. There is no delta x sub I squared in the second term, but we can still divide it out by taking delta y sub I squared and dividing it by delta x sub I squared. Why would we do that? That gives us a fraction. That's ugly. Well, we'll see why in a moment. One nice thing we can do with this is we can factor out or not factor out, but we can reduce this radical because of the multiplication. The square root of delta x sub I squared is delta x sub I. And then we're left with the square root of 1 plus delta y sub I over delta x sub I, both being squared. Okay? We've gotten this s value that is approximately equal to the sum of n line segments. And now we say that s is exactly equal to this whole thing as long as n goes to infinity. Why? You should know why. It should be obvious at this point why we're letting n go to infinity. And when we do let n go to infinity, we get that integral instead. Okay? So instead of delta x, we're going to use dx. Instead of delta y over delta x, we're going to use dy over dx. Oh, wait a second. That's the same thing as the derivative. So we're going to put this derivative inside this radical. So this is a bit strange, but we take the square root of 1 plus the square of the first derivative. We integrate that, and that's going to give us our arc length. So this is just using the distance formula an infinite number of times over infinitely small line segments. So if we're going to try to find the length of that parabolic road, we have a equals -1, we have b equals +1, we've got f of x equals x squared, which means that f prime of x equals 2x. So that means that f prime of x squared equals 4x squared. So s is going to equal the integral from -1 to +1 of the square root of 1 plus the square of our derivative dx. Now we can look at this and scratch our heads about how we can integrate this, but we're not going to get very far unless we know a process called trig substitution. And it is possible to integrate this using trig substitution, but we haven't learned that yet. So I'm going to just go ahead and say set up but do not solve. There is an integral expression that gives us the exact length of the parabolic road. Maybe I'll go ahead and use a calculator to get a quick approximation. I'll paste that in here so we can see. See that that integral works out to be about 2.95788. 2.9 or so. We go back up to our approximations. That 2.95 with n equals 8 was a little bit too small. 2.95 was a little bit smaller than the actual answer of 2.95788. 2.96 would be a better approximation, but it was pretty darn close. Okay, so anyway, the calculator told me that this was equal to, I'm going to say this is approximately equal to.